Hey everybody, Paul Abernathy here. Welcome to a coffee hour with me, Paul Abernathy. On today's episode, we are going to talk about branch circuits to motors, a single motor, and we're going to kind of explain a little twist that sometimes can appear on an electrical exam, but you most certainly have to know how to do it in the field, is what happens if we have an elevated ambient temperature. So how do we have to take that into consideration? Well, most of you who've watched my videos before know that when you're sizing for the branch circuits for a motor, that you're basically going to go to 430.22. And it tells me that if that's a continuous duty motor, that I'm going to take it at 125% of the FLC. Now, the FLC is full load current. That's what we're going to see back in the tables that are in the back of Article 430. 247, 248, 249, and 250, those are specific tables that have the FLC value, the full load current, which is different than the amps that are on the nameplate, which we refer to as the FLA, to make it easy to distinguish. But those that are on the nameplate have power factor figured into them, things like that. So we're using the FLC for sizing conductors, okay? So we're gonna be looking at that today and kind of breaking that down, but different than what we've done before, whereas typically on an exam, they're just gonna say, here's the motor's FLC, what are the size of the conductors? And you're gonna go, okay, well, they can't be less than 125%, because that's what it says in 430.22. But what about that ambient temperature? And again, many people think that, well, since it's in 430, that we just get to ignore the ambient temperature. Or if you had more than 3 current carrying conductors, do you have to make some type of adjustment? And the answer is yes to all that. The conductor is still the one that's exposed to that condition of use. So we have to do something for that. So what we wanted to do in today's coffee hour right there is we're going to talk about what happens if we have a temperature correction that's involved in our traditional branch circuit that's going to a motor. So I wanted to give you that little quick lesson today here, Labor Day weekend. So let's go on and get into our lesson. Okay, as we get into our lesson again, as always, you can post comments down whatever platform this video is being shared on. Also, don't forget at the top, you see that we're still running what we call the Friday sale, but we're running it perpetually, and that is 50% off our Fast Tracks 2 video subscription. That is a platform where you're going to see a lot of exclusive videos, a lot of content that's not going to be available on other platforms like YouTube and whatnot, that type of thing. So check that out. We'd love to have you subscribe to that platform. And if you're not a student of ours, check out right there, fasttracksystem.com. We've got courses on grounding and bonding and all types of other things to help you learn the National Electrical Code. All right, so we're going to do this lesson today. And so here's our question. A motor is at the end of a 25 feet of a conduit run that contains only 3 conductors at the expected ambient temperature of 115 degrees Fahrenheit. Okay, and we say 3 conductors. There's no neutral needed here, and it's using the conduit as an equipment ground, which is permitted by the NEC, whether you do it or not. In our example, it is. So we don't have more than 3 current carrying conductors, but there is an ambient temperature of 115 degrees Fahrenheit, which deviates from the 86 degree Fahrenheit or 30 degrees Celsius ampacities that are given in table 310.16 of the NEC. So we know we got to do something there, right? This goes on to say, what are the minimum size THWN copper conductors required to serve a continuous duty, design B, 25 horsepower, 208 volt three-phase motor. Okay, so we have all the variables here that we need in order to size these conductors. So the very first step that we should do is that before we even get into the ambience, we got to say, all right, I have to find the full load current. And in order to find the full load current, the first thing you're going to do is you're going to go to your National Electrical Code, and you're going to go back to the tables. And in this case, you're going to go to 430.250 because it is a three-phase motor. And you're going to go to the 208 volt column and drop down to the 25 horsepower value, and you're going to see that it is 74.8 amps. Now, I'm going to say that, but we're going to go look at it. So here we are in the NEC, and we're going to drop down to 250, table 250 right here, and I'm going to try to pop this out for you. All right, so this is what we got. So we're at 208, so this is the one we're working with, and we want to come down, and it's 25 horsepower, which is right here. So you draw your line over, and of course we're drawing our line down, and that is where we get right there. So our FLC, full load current, and that stays consistent. That's why we use it for conductors. That's why we don't use nameplate here. We use the tables because regardless of motor changing, as long as it's this horsepower, then it's going to stay consistent, and we don't have to worry about sizing conductors too small. We stay consistent here. A motor might get more efficient, better power factor, all these type of things that could change the nameplate. But these values here in the table stay consistent. So that means that if there's a replacement of a motor or something, that we stay consistent with the conductor sizing, as well as the other rules that use the FLC, like the short circuit, ground fault protection, things like that. Okay, so there we go. So there's our 74.8 amps that we're going to be working with. Okay, all right, let's get back to the lesson. All right, so we established that. We're good to go. Now, same variables. Next step is we have to identify the proper temperature rating of the THWN copper conductor. Now, this is interesting because THWN, y'all know the T stands for thermoplastic, H stands for heat, W stands for wet, and N stands for nylon. Okay, so this differs from THHN in the fact that there's no W in there, and THHN has two H's. And two H's means high heat, means 90-degree rated insulation. One H means 75-degree rated insulation. Now, you're probably all familiar with the wire that you buy. It'll be THHN/THWN-2. Well, that -2 signifies that it is also 90-degree rated insulation, which is important when we're doing a ambient correction here later. But in our case, it's only THWN. So what that means is that it is only rated at 75 degrees C, and we can verify that, and we will go verify that, but that is going to be 75 degrees, so we do not get the ability to use the values, ampacity values in 31016 from the 90-degree column. Why? Because our insulation isn't rated for 90 degrees. It's only rated for 75 degrees. Okay, so that's important things to always remember in this. So we're going to go to 310.4a, and we're just going to verify what our rating of our THWN is. Okay, so let's just go back to the code, and I'm going to take us back. Bear with me here. I'll run us all the way back to 310, and then I'll get us in 310.4. Okay, hard to see this table, but you'll be able to see enough of it to be able to understand where we're at. So we're going to kind of go down the list here, and we're looking for THWN. There's THHN, there's THW, THW, there we go. THWN, dry and wet locations, 75 degrees C. Now see that -2 on there? That's 90. Significant. And to be honest with you, just on an exam would they pull this type of thing where they only rate it as THWN. In the real world, chances are it's going to be THWN-2, which again, that means that I have the luxury of using the 90 for adjustment or corrective purposes. That ampacity, at the end of the day, still can't exceed the rating of the terminations, which are, in this case, are going to be 75 degrees C anyway, but it gives you more room to work with by being able to use a 90-degree ampacity than what we're going to be locked into, which is the 75. Okay. All right. So that kind of establishes that. So we know what we'll be working in. So we're obviously going to be right here in this 75. Okay. All right. So let's move on to this. So as the results is 75 wet or dry, 2023 NEC. Again, whether you're following in an earlier edition, it's still 2020 code. It's still going to be 310.4a. If you're in the 2017, it's probably going to be 310.104 in the NEC. Okay. Same information, just kind of got moved around a little bit. All right. So now we've got all that. We're putting all the pieces together. The next thing we go is, okay, let's deal with this ambient correction, right? So we're dealing with 115 degrees Fahrenheit. So we have to select the proper correction value to be used in our example, because yes, we do have to take the ambient. You can't just discount it and get rid of it, disregard it. It's still a condition of use that we have to take care of. Now, notice we don't have more than 3 current carrying conductors, so we don't have to worry about that in our equation, but it would work the same way if it was in the equation. Same way that we're going to work this one. It's just you would have both in play rather than just one item in play. Okay. All right, so we're looking at 115. All right, so what we're going to do is we're going to go to table 31015B11 in the 2020 that's actually the 2023 edition of the NEC, but it would be 310.15B1 in the 2020 edition. Doesn't matter. It's going to be the same location. So let's go do that. All right, so I'm going to go here and let's go to 310.15. And I'm going to get us down to, all right, so here's B11. Again, we're talking 2023 edition of the NEC. We'll expand this out so we can see it a little bit better. And so in our situation, we're dealing with, obviously, we're other than 30 degrees Celsius and 86 degrees Fahrenheit. So we have to make this ambient temperature correction. So we're dealing in Fahrenheit. So we're going to go to the Fahrenheit column, which is right here. And we're going to go down. And it looks like we're right here. We're at 115. So we're 114 through 122. Now, here's where people get confused. If we were using 90 degree rated insulation, then we would be able to use the modifier here. But we're using 75 degree rated insulation. Remember, this is based on the temperature rating of the conductor. So we're still locked in the 75 because our conductor's rated 75. So we're going down here and it looks like our modifier is going to be 0.75, okay? So keep that in mind. That's what our modifier is, all right? So we'll come back to our lesson. And there we go. Our modifier is 0.75. All right, so first thing we want to do is, what if we were looking for the conductor? Now, this is typically what you get on an exam, right? If they don't give you the ambient. I'm going to show you how this can differ in conductor sizing. If they don't give you the ambient, then it's pretty straightforward, right? You take the FLC and you multiply it by 125% because that's what it says in 430.22. Pretty straightforward, right? So, and it also says not less than 125% of the FLC. Could it be higher? Yes, it could be higher, but it's not to be less than 125%. That's what it says in 430.22. And we'll go validate that. So let's go to 430.22 just so we can make sure that we're covering all our bases here. All right. Let's see, 430.22 right here for a single motor. And this is what we got right here. Here's the language right here. It says conductors that supply single motors used in a continuous duty application shall have an ampacity of not less than 125% of the motor's full load current rating. Okay? So, whatever happens, even after we do some adjustments or corrections, we still have to have a conductor with an ampacity value that is 125% of the FLC. So no matter what we do, it can't be less than 125%. The conductor's ampacity can't be less than 125% of the FLC. And as you saw earlier, we already know what the FLC is. So easy peasy for us to start working this. So I wanted to validate that in 430.22, okay? All right, so if you remember, it was 74.8. That was our FLC, and we're going to multiply that by 125% because that's what it tells us in 430.22. So I'm going to do it here just to make sure our math is right. And that gives me 93.5 amps. Okay, so I have to have a conductor that has an ampacity under the 75-degree column, because we're working with the limitation of the conductor, which is THWN. I have to have a conductor that's at least 93.5 amps. Now, on an exam, if they don't ask you about the ambient, or there is no adjustment for a number of current carrying conductors, then it's simple, straightforward, right? Then you would just go to the 75-degree column, and you would choose a 3 copper, which is good for 100 amps. Easy peasy, right? Okay, that's probably what you'll get a lot of times on your exam. But what if, and in our question, we have an ambient we got to take into consideration? Must take it into consideration. All right, so that means that if we were to take that 100 amp conductor, which a 3 is good for, and now we use the multiplier for the ambient correction against that, what would that give us as an ampacity? Well, 100 multiplied by 0.75 will give me a conductor that's only good for 75 amps. Well, that's less than the required 125% conductor sizing based on 430.22. So we already know that's not going to work for us because of our condition of use, okay? So just remember the two. On an exam, if they don't ask you for the ambient and they don't say anything about more than 3 current carrying conductors, this is it right here, straightforward. Now, of course, also, this actually came from, this is NEMA. It shows the different designs, different motors, and all this type of designs and all. All this stuff's available from NEMA, but you can also get it from what's called the engineering toolbox as well, if you're interested in seeing the different ratings, the different designs, all the stuff. You can even screen capture this if you're interested. This kind of just shows you some of the design. All right, back to our question. All right, now that we have the ambient, we're going to work this thing how it's supposed to be worked. So that FLC is 74.8 amps. We're going to multiply that by 125% because we know that that's our starting value. We can't be less than that. And then we're going to use division to go up and look for a conductor. We use division at this point to go up. Now, once we have the final number, we can use multiplication to check our work, but we're going to use division to work our way up. So in this case, it's 74.8 amps times 125%. I'm going to do that with you here. So 74.8 times 1.25. That is 93.5, which we've already done. And I'm going to divide that by 0.75. And that gives me 124.66, which we're going to round to 125 for simplicity's sake, because that .66 ain't going to do us much good. All right, so 125 amps. So now, we would now go where? We're going to go to 31016, and we need to go to the 75-degree column because that's our terminal limitation. I mean, that is what our conductor limitation was because we didn't use 90-degree rated conductors. We used 75. So let's go to the code really quick. And I'm going to go back to 31016. And let's get to the ampacity table. I'm going to throw this up on the screen as big as I can make it. All right, so we're in copper, so we're good. And we need to come down here and find under column, 75-degree column here. We need to find a conductor that can handle 125 amps. All right, well, it looks like it's right here, and that is a 1 gauge, which is 130 amps. Okay, so how do we check our work to make sure that after the ambient correction, this conductor is now worth 130 amps. After the ambient, are we still going to have enough to be at least 125% of the FLC, right? So let's see what that is. So let's do this. So let's do the 130. Now I'm going to use multiplication because we're looking going down, time 0.75, and that equals 97.5, right? Well, 97.5 was perfectly fine because if I go back, let me take you back to the lesson. So we have 97.5 conductor. And if we scroll back here real quick, we see we needed to have a conductor that at least handled 93.5. So obviously 97.5 is good enough to be able to handle it. So boom, boom, boom. So that's it. So to answer that question, conclusion, 430.22 says the branch circuit for this motor has to be at least 125% of the FLC. Now, even after the adjustment or corrections, oh, and by the way, if I had, people ask me this, let me go back real quick. If I had a number of current carrying conductor equation in this as well, then it would have been simply 74.8 times 1.25 divided by 0.75 divided by whatever that adjustment would have been, whether it's 80%, 0.80, would have been the same scenario. And I can show you that. Let's just say it was 80%. So I go 74.8. I'm going to multiply that by 1.25 equals 93.5 divided by 0.75 equals 124.16 divided by 0.80, 155, and we would have had to go and find a conductor that's good for 155 amps. All right, and then after the adjustment and correction, we would have been making sure that we had a conductor again that was at least 125% of the FLC of the motor. So we're meeting the rules in 430.22, and we're adjusting or correcting accordingly to make sure that we're not going to be causing any problems to the conductor or the insulation of that conductor from heat buildup, things like that. Make sense? Okay, so that's how we equate it, and it's pretty straightforward. Either way, the way we did it, the size of our conductor is going to be 1 gauge copper instead of 3 gauge. Why? Because we had to take into consideration the ambient temperature, okay? So now if we were to look at this from a illustration point of view, remember what I said, if we did not have any ambient temperature in this equation, so now I tell you this one because of being ready for exams, okay? If there was no question about ambient temperature or number of current carrying conductors exceeded 3, then it's pretty straightforward, right? 74.8 amps came from the table. Then you apply the 125%. So that's, and ignore the A there because it's not A, it's just 430.22. So 74.8 amps times 125% is 93.5. Remember, small conductor rules don't apply to motors. We get that advice from 240.4G. It's referenced by 240.4D, which is the small conductor rules. And then we go to 310.16 and we find a conductor under the 75-degree rating, and it was 3. That's all you do if that's what the question is. But ours was obviously a little different because we had the 115 degrees Fahrenheit thrown in. So we can't be smaller than 125% of the FLC. So same thing applies. The only difference here is 74.8 amps times 1.25 divided by 0.75 is the 244.66. We're going to round that to 125. And we go to the 75-degree column, and we have to find a conductor that can handle the 125 amps. And of course, our 1 gauge is good for 130. And we can use multiplication to verify that by simply taking the 130, multiplying it by 0.75, and you'll see that we have a conductor that is, I believe it was 97.5, easily can handle the requirement in order to be able to handle that conductor's ampacity at 125, the FLC at 125%. We were okay for that application, all right? Does it make sense? 97.5 is greater than 93.5. That conductor is perfectly fine, but we had to jump up to a 1 gauge to make that happen. So some takeaways from today's lesson. Make sure you always read the question. Remember that small conductor rules don't apply when it comes to motors. Remember, when something says at least, that's a minimum. Okay, so when it comes to those motors branch circuit, it says has to be at least 125% of the FLC. At least, remember that. In most electrical exams, they're probably not going to have a condition of use like more than 3 current conductors or an elevated ambient, but you know how to do it now, so you'll be prepared for that if you have to. Also, remember, in our equation, voltage drop did not play a role. People want voltage drop to play a role in motors all the time, but you remember motors have overloads, so even if it was a condition, it's not going to overload the conductors. So now, should you take voltage drop into consideration? That's a very prudent thing to do, but it played no role in this exam question. And typically, even for these applications in the NEC, voltage drop is a recommendation, it's not a requirement, okay? Except for sensitive electronic equipment and fire pumps. Other than that, it's just good electrical design, that type of thing. But again, on an exam, they should not mandate you to do voltage drop because it's not a mandate in the NEC, unless it's those conditions I just said. Fire pumps in a sensitive electronic equipment, all right? So there you go. That's pretty much all you need to know to answer those single motor branch circuit questions, right? If you really want to learn the National Electrical Code, we recommend you get into a good NEC structured program like our Fast Tracks program. You can watch videos on our program to see how it is on our website. The URL is right there. Check it out, fasttracksystem.com. Also, remember, you can get 50% off Fast Tracks Tube. It's going to be blowing up. Y'all all are aware that our new studios in Virginia, we're going to be doing videos weekly, multiple videos, a lot of training, and we still got stuff we're releasing for the rest of this year. Check it out. Best value, cuts the price in half, and you also get access to the Wednesday night sessions every 2 weeks by being a member of Fast Tracks Tube as well. Even if you're not a student, you can come to the Wednesday nights and join in and learn something in the process. So, hopefully you got something out of it. Very quick video explaining ambient temperature correction and how you would apply it and how to do the calculation even if that wasn't a condition. It's pretty straightforward. It can't be less, the conductors for a single motor can't be less, a continuous duty motor can't be less than 125% of the FLC. You do not use the nameplate amps when you're sizing conductors, okay? All right. Hopefully you got something out of this, folks. Till next time, thanks for joining me on a coffee hour. I guess it wasn't an hour, but hopefully you got something out of it. Till next time, stay safe. God bless.